lattice point. So then the operator is acting on this Q trig here, or like the fields in the bulk, you know, phi and phi dot or whatever. And then we saw that we could represent those on any two of the boundary Q trigs. And so we saw that was sufficient to give us radial commutativity, radial locality within this code subspace. So the first thing I'm going to do today is give a sort of generalization of this model that allows us to now have many degrees of freedom in the bulk and many degrees of freedom in the boundary, but it's still exactly soluble. So it's not, you know, it's not going to have all the features of holography, but you know, but it'll have more of the features of holography in some sense. So the idea, and so what I say will be based on this happy paper. So this is me and Arlo, and then this is Pastovsky, Preskal, and Yoshida. And this is the ordering we use because it's too much fun. But I should say that, you know, the correct ordering is P, Y, H, A, P. Okay, because Pastovsky and Yoshida were the real heavy lifters on this project. But this is so good, you have to. All right. So the idea is that now the CFT will be n qubits, and the bulk effective field theory will be a 2 to the k dimensional code subspace. So roughly speaking, what you should think of this code subspace as being like the set of low energy states in the CFT. So say states whose energy is less than n squared. Now technically that's not quite correct, because we'll see that I'm going to define it in a way that respects a large part of the conformal symmetry, whereas saying it directly in terms of the energy doesn't. So what I really mean is that you should think of this as being like the conformal image of the set of low energy states in the CFT, right? Because of course something can be high energy just because it's near the boundary, but that's kind of a boring kind of high energy. I mean, that still should be described by bulk effective field theory. I'll also be including that physics within the code subspace. So you might intuitively think of it as being like a sort of no black hole subspace.
By n square, you meant small n square?
Sorry, big n square.
Big
Yeah.
N.
So maybe I should say C or something, but that's misleading to us.
Basically, what you mean is sort of states which are dual to simple single trace operators.
Yeah, that's right. That's right. So I mean, in principle, that you should, you know, if there are strings or whatever, you might want to think of it as including the classical strings and so on, but not including states with black holes. We'll discuss later how to think about the black holes also in this model, but let's start first not having the black holes in the code subspace. It's already interesting enough like that. Okay. So to describe this subspace, clearly what I need to do is I need to give the wave function. So there are n physical qubits on the boundary, and there's a complete basis for the code subspace, which is labeled by k qubits. And I have to give you this. If I give you this, then I've clearly described for you.
Sorry, say again, what is this? So the draw,
So the tilde. So remember we had this kind of notation.
Oh yeah,
right?
I see.
Yeah.
For the code subspace.
Yeah. So remember, I tilde up here was a complete basis for the code subspace. So here I guess I called it J instead, but now the code subspace is labeled by a state of k qubits.
Okay.
Because we have a 2 to k dimensional
I got it.
code subspace.
Does this this type of scalar product makes sense because the dimensionalities are very different. Ras and kits.
Oh, no, yeah, because let's remember, right, so in the free trade model, we have equations like this, right? I'll just write the first one.
Small n is less than k, so you can.
Yeah, so this is the analog of that equation that I was suggesting.
I'm sorry.
That's good to be clear. Okay, and then, so the thing to notice here is that we can think of this as just defining some tensor, which has two kinds of indices. It has I indices and J indices. And so if I can describe that tensor to you, then I've described for you this subspace. So the idea is to build T with a tensor network. So let's just quickly remember how tensor networks work. So the idea is you start with a bunch of little tensors, like say here, or, so each dot here represents a tensor with an order 1 number of indices. And then when you draw a line between the dots, that indicates that you're contracting the tensors. So maybe, say here, I don't know, let's say each tensor in this set will have 4 indices. So then, and then the network tells us how to sew the indices together. So maybe I'll contract those two. Maybe I'll contract these two, these ones, maybe these ones. And then of the uncontracted indices, then we can pick some subset, say these ones, to be the J's, and then we can pick some other subset to be the I's. And so that kind of diagram allows us to build tensors with many indices out of component tensors with an order 1 number of indices. So that's nice, because then to define this, I just have to draw a picture once I've told you what the constituent tensors are. So I should maybe comment just right. So there's some ideology that goes with tensor networks. So I'll just say in case you haven't heard it before. So the ideology is that when you're studying many body quantum systems, the Hilbert space is gigantic, right? So say if you have n spins, right? The Hilbert space is 2 to the n dimensional, and most of the states in the Hilbert space are completely uninteresting usually. They just have nothing to do with physics. So for example, if you're trying to, if you have a local Hamiltonian for the spin system and you're trying to find the ground state or the low energy excited states, these will be very atypical states in the Hilbert space. So what tensor networks do is they give you a way of parametrizing subspaces of the Hilbert space, or let's just say subsets. Let's not worry about linearity. So if you draw one of these networks, then you've replaced the full coordinates on CP to the 2n with some much fewer parameters, right? So you're describing a very small subset of the states in the Hilbert space. And then, well, the nice thing about tensor networks is that they usually seem to describe the interesting subset of states, at least if you're concerned about low energy states of local Hamiltonians. So this is the core of a revolution which is happening in numerical many-body physics, where people are using tensor networks to do many-body computations which were previously considered to be completely intractable, because they let you sort of sidestep this exponential growth of the dimensionality of the Hilbert space in the many-body system. Okay, so all right, I just have to say that.
How do you arrive at the name? What is the network?
Yeah, good. So there's kind of an art to it. It depends. So you have to have some intuition about the system. In particular, you have to have some intuition about whether it's gapped or not. But then the idea is that you keep the geometry of the network fixed, and then so usually if there's a symmetry, then you can take each tensor solve a variational problem to determine the components of the individual tensor. By, so say you minimize the energy within the, and there are cases where you can prove, that when you do that, the overlap with the ground state is non-zero in the large head limit. And it's kind of remarkable, So, it's still a young field, but, already the developments are very exciting, and I suspect that within, 10 years, this will be the predominant way of studying many body systems numerically.
I missed, did you define what a tensor network was?
Yeah, so that was the
define runs model.
Yeah, so the idea was you have you draw a bunch of dots. Each dot represents a tensor with an order 1 number of indices. In this case, each tensor has 4 indices. And then anytime you connect the lines, that indicates contraction of the indices between the tensors. And then whichever ones you don't contract are outputs of the network, or you can do some as inputs and some as outputs, which is what I'm doing.
So that's a tensor. How does it connect to a state?
I'm sorry. So we're trying to generalize the 3-qubit code to a case where there are n qubits in the CFT and a 2 to the k dimensional code subspace. Previously we had 3 qubits and a 3-dimensional subspace. So to do that, I have to tell you the wave function of a complete basis of the subspace in terms of the physical qubits. So, but this just defines some tensor with many indices. So the idea is I'm going to construct that big tensor by taking a bunch of small tensors and then contracting the indices in a way that...
Which side is the actual states and which side is the code subspace?
So n is bigger than k. So this is the complete basis for the CFT. This is the CFT. So that's the real Hilbert space, the full Hilbert space.
And the J labels have nothing to do with the idea.
Nothing to do, yeah. So the analog of this formula yesterday was this one, or then the other one's like it, right?
Yeah.
So this is like a J, and these are with the I's.
So the way Vidal did this Mera stuff is
Yeah.
to have some variational wave function to be constructed out of these entanglers, starting from some completely productive kind of state.
Yeah, that's
and then
right.
you keep doing that.
Yeah,
so
that's
there
right.
will be something like a 2 going to 1 kind of thing.
Yeah.
Or it could be more complicated in Mera.
Mira is an example. Mira is a particular example of this.
So here the idea is pretty much the same, that you start with some very simple state and you keep, or how do this network of points appear?
Well, so I just drew some stupid example here. I mean, of course, tensor network is a very general concept, right?
Okay.
So you can draw any graph, and you can interpret the vertices as tensors, and you can allow some of the legs to go out, and then that defines a tensor network. And if it tell you the states, then the tensors, then it defines a state or a set of states.
But some of these have to be I legs and some have to be J legs.
That's right. So that was what. There's an I here. Sorry, it's not very clear. Yes, the idea was say these are the J legs and these are the I legs.
So these tensors have 2 kinds of indices.
2 kinds of indices. Yeah.
Even the contracted indices are...
Well, I would say that the tensors. So with the tensors, the indices could all be the same, but you just pick some of them. So you pick. So
Pick some subsets.
there are indices that are contracted, and there are indices that aren't contracted. Okay, that's invariant.
Yes.
Now, amongst the uncontracted indices, we can now choose, if we like, some of them to view as inputs and some to view as outputs. So here in this language, I would say these are the inputs. We say which bulk state we want, and then the tensor network spits out for us the wave function in terms of the physical qubits.
So what's confusing me is that the J's and the I's could run over completely unrelated sets of indices.
Yeah, that's right. But no, I didn't promise you that these tensors were symmetric. It could be that they're,
Okay.
the only rule is anytime I contract 2, then they have to.
These contracted indices could also be of a third sort.
Oh yeah, no, in general it could be completely arbitrary. Yeah.
So it's not saying very much so far.
Yeah, right. I mean, it's a very general idea. Obviously, in specific examples, there are answers to these
So
questions.
the contractions can be between the I's and the J's, or only amongst the I's and only amongst the J's?
No. So to be clear, so the I's and J in this formula, these are uncontracted indices. So maybe let me draw a simpler example. I think that one was there are two tensors, okay? Tensor 1 and tensor 2. And each of them has some fixed number of indices. Now, so one operation that now that we can do is we can contract some of the indices between these two tensors.
And these indices could be of a third sort. Not
Yeah,
either
they could all be
either,
different.
any.
Yeah, they could be anything.
They're in a
The
different
only
space.
rule is that they have to, the ones that are contracted have to have the same range.
Yes.
Yeah. Okay, and then there could also be some vertices sticking out. Okay. So this defines a tensor, just a tensor. Now, if we want to interpret this as defining states, then we have to decide which of the outgoing legs we're going to view as i's and which ones we're going to view as j's, and we can do whatever we want to some extent. Now, if you want to view it as defining a subspace, then you need sort of fewer of the inputs than you need of the outputs. At least if you want it to be, if you want these to be all orthogonal. But I mean, with generic tensors, they won't even all be orthogonal. So you can just, you're free actually to choose whichever ones to be inputs and outputs as you want in general. And you'll always define some set of states in the output Hilbert space, labeled by the input. I'm interested in the case where this is an isometric embedding, meaning that these states are orthonormal in that Hilbert space, and so that puts constraints on the tensors.
But in general, as you're saying, you can then think of this tensor as defining a map from 2 to the k-dimensional subspace to a 2 to the n, and,
Yeah.
and then your tensor network tells you what the map is.
Yeah, and actually in a lot of what we do, there's going to be, there's a lot of malleability here. So it's very convenient to sort of sometimes think about some things as the input and other times as the output.
I'm sorry, Dan, you probably said this, but I understand there's a tensor, but now you're building it out of like products of smaller tensors.
Yeah.
What is the point of that?
Well, but the indices are contracted, so it's not really products.
I understand. Contractions of smaller. But why are you doing that?
I think the smaller tensors must be the generalization of the unitaries that you use.
Not quite, because those unitaries will be very complicated, right? So the idea is, we want to just, so these states, in general, will be very entangled states, right? So low energy states of the CFT will be very entangled from the point of view of the fundamental CFT degrees of freedom. So you could just say, oh, there's some big tensor and that describes these states, but I mean, come on, right? That's not helpful. So the thing that's helpful is that you can graphically represent the entanglement structure of these states, by giving an algorithm that builds this out of small pieces.
Daniel, just to clarify, the set of states you get, I think, is output on the left-hand side. That's actually measure 0 in the full space, right?
Yes, absolutely. Yeah, absolutely, because it's a subspace of lower codimension. Yeah, that's right. Yeah. That was why when I talked about constructing the ground state in these many body systems, I said that you can get an overlap with the ground state, which is order 1. Right. So that's already pretty good, but that's not an exact statement.
Okay, yeah.
Just go back to Gautam's question.
Yeah.
One of the reasons perhaps you wanted to think of building this tensor out of smaller elements is that the way ultimately you relate it to our discussion yesterday of error correction,
Yeah.
and that'll, if you make it out of smaller elements, it might become clearer how you're going to protect, right, against erasure and so on.
Yeah, that's right. Right. Yeah, that's certainly what I'm going to do. Yes. But there's this more general point of view, which is that low energy states of many body systems are very special, and this seems to be a much more efficient way of parameterizing them, than just giving this wave function, right?
You think if you draw a graph from that, the entanglement of the state is manifest?
Yeah, that's right.
It's not to me, but
Well, it should be maybe after you see the pictures.
Okay.
Here this is just some.
Yeah.
Right. Okay. Let's do a trivial example. Just maybe that'll help. Okay. So here's one interesting thing we could have. So we could consider the theory. We could consider the states 0, 0, plus 1, 1, and 0, 0, minus 1, 1. Right. Then this state we can view as speaking, if you have some more complicated thing, right, like that, then people who are sort of closer in the graph will be more entangled than people who are further in the graph.
So what would the map? Is it state goes to 0, 0 or 1, 1 correspond? The unentangled states.
Oh, that was the one I drew. That's like that. Yeah.
Those states
So
will be
this is like J. This is like J goes to I, J1 goes to I1, and J2 goes to I2. So that's the trivial tensor network. It's the identity.
I1 is 0, 0 and I2 is 1, 1.
Yeah, this could be 0, 1. This could be 0, 1, and it just maps to 0, 1, 0, 1.
But suppose I wanted to map to a larger dimensional space.
Oh yeah, you can just hold this one fixed, right? So you can just say this is always 0. So you can just feed in.
Right. I think in the
So
example where the 2 going to 1, you only generate the 2 states written above as your output,
Yeah.
J, and then your tensor will give you the overlap of those 2 with 0, 0, 1. Right?
yeah, well, so in this picture, so here the tensor is right. Let's define this to be 0 tilde, and define this to be 1 tilde. Okay. So then then this defines the tensor, right? Because it says if I have a 0 here, right, then there's a 1 if it's 1, 1,
Right.
and there's a 1 if it's 0, 0, and then it's 0 otherwise.
Otherwise,
Right, and then if I put a 1 here, then I get a 1 for 0, 0, and a -1 for 1, 1, and a 0 otherwise.
But suppose I just want 1 to go to 1, 1, sorry, 0 to go to 0, 0 and 1 to go to 1, 1. That also defines some tensor.
Oh,
I'm not seeing the difference between the entanglement.
sorry, so you said you want...
0 to go to 0, 0 and 1 to go to 0 tilde to go to 0.
Well, that depends on the choice of the tensor. Right?
Exactly.
So, so right, there is a tensor that doesn't... Well, no, right, so that depends on what the tensors are, right? It's not a guarantee of entanglement, but it's necessary for entanglement.
Nice.
So like in this one, it's definitely not going to be entangled, that's the thing. And so then, right, and then once it's possible for it to be entangled, then this minimization procedure will pick the tensor so that it is if the ground state is.
I didn't understand the example.
Oh, well, okay, Shiraz was suggesting that I just put, I do that.
Yeah. I want an unentangled example in the same graph.
Yeah, you're right. So that would mean that this tensor was kind of a trivial tensor. Yeah. Okay. So in general, right, so now that by this you should already start to see the difference between gapped and ungapped systems. Because you see in this picture, right, the correlation between these guys is controlled by sort of how far back you have to go. And so if you imagine that you have a correlation function that falls off quickly at large distances, then the depth, you can imagine the depth of this sort of goes down to the mass gap and not further. Whereas if it's the CFT and there's sort of long-range correlation, then you sort of need this continuing nested structure to continue further and further. And that's what Neuro was designed to do. And you'll see that our networks are going to be like that too. So in particular, they won't be gapped. Okay. All right. So that. All right. So that's just tensor networks 101. Now the tensors I'm going to use are a special kind of tensors, which are called perfect tensors. As the building block tensors. So definition. So a tensor with 2n identical indices. What do we put here? Indices is perfect. So what that means is that any so let me draw a picture. So say here we've got a perfect tensor with 6 indices. So balanced bipartition means a split into 3 and 3. So for one thing, it says that this is a unitary transformation going this way, but it also says that that is also unitary, or any other split into 3 and 3.
This is quite a restriction.
It's quite a restriction, yes. And in fact, it's such a restriction that it's not obvious that perfect tensors should exist. And indeed, if we fix the number of indices and we fix the range of the indices, they don't necessarily.
Sorry, if you fix the indices.
If I fix the number of indices and I fix the range of the indices, then they may or may not exist. There are cases where they don't. But there are also cases where they do, of course, I wouldn't be telling you. So in fact, let me give you a simple example. So one example of a perfect tensor is just the encoding map of the 3-Qtrig code. So this is a 4-index tensor. So this is T, I1, I2, I3, J. So it's a 4-index tensor. And I claim that indeed if you split this into any pair of the indices, it's unitary. And so for example, if I do, right, so say I do 1 and 2 and then 3 and J, then in fact the unitary will just be this U1, 2 we were talking about yesterday. Right? So
Daniel, I'm confused about something. I thought you said the indices have to be identical, but in this tensor they're not identical. Like one of them is a logical index and the other is a physical. The 3 of them.
no, but that's interpretation, right? That's interpretation. Each one is a Q trait. That's all I meant by identical. The ranges are the same. Okay. So let's just confirm. Since this is simple enough, let's just confirm that it's actually a perfect tensor. So remember, J tilde is U12 times I1 times chi23. Okay.
J.
I forgot one thing. Let me see. I need to put a square root of 3 here.
That'll be J1, right?
What?
J tilde is I1.
Oh, sorry, you're right. Yeah, J. Yeah. So then we can just compute. We can just compute this, right? We can just take the inner product of this with I1, I2, I3 with this, right? And so that then so remember chi was this was 0, 0 plus 1, 1 plus 2, 2 over square root of 3. So then the square root of 3 here is designed to get rid of that square root of 3. And then this I3 is going to collapse this entangled state onto just I3, I3. Right, and then that'll right. So that'll just that'll just give us a 1 over square root of 3. So then indeed this Ti1, I2, I3, J is just I1, I2, U12, J, I3. So it's a unitary. And then clearly if I can do it for U12, remember there's also U13 and U23. So this will be true for however we split up the indices. And so that should also convince you that the existence of these perfect tensors is closely related to error correcting codes. So basically that's how you find them, is you find error correcting codes and it gives you perfect tensors.
Does that mean, John, what you said around, you can't always have error correcting codes?
Yeah, right, which is true. So for example, you might ask, why did I do 3 Q traits instead of 3 qubits? And the answer is because there is no 3-qubit code. Okay. Now, these perfect tensors then have a nice property. So I'm gonna, well maybe let me say, so the perfect tensor which I'm going to use is going to be one with 6 qubits. So, and it's the encoding tensor of the simplest qubit code, which is a 5 qubit code. So there's a 5 qubit code where you encode 1 qubit into 5, and then you're protected against the erasure of any 2 of the qubits. So that's the code that I'm going to use. That's the tensor I'm going to use. So that's why I'm drawing 6 here. So now say that I have some operator, which is a 3 qubit operator, and it's contracted with this perfect tensor T.
And sorry, in this example of one qubit going to 5,
Yeah.
these are qubits, right? Not
Qubits. Yeah. 0 or more. Yes.
Okay.
So what I'm saying here is true for any perfect tensor, but I'm just explaining why I was drawing 3 to get you in the habit of seeing a 3. So for any operator, if you multiply it by a perfect tensor, then you can actually replace this by putting the tensor here, and then having a different operator here, O prime, where you just do the obvious thing. So O prime is T dagger O T. Right, so then I've used the fact that T is unitary in this channel. But then because the tensor is perfect, I can do this sort of whichever 3 indices I want. So anytime I have an operator that's acting on 3 of the indices of the perfect tensor, I can use this to replace it by an operator which is acting on the other 3. So this is called operator pushing, because you can push the operator through the tensor at the cost of rewriting it. Okay, so that's the tensor network machinery. Now we want to talk about the actual tensor network that we're going to use to do holography. And so for that I need to do the computer. Because yeah, this is not the kind of picture you want to draw by hand. Alright, so maybe we should get the board lights. I think I heard it. Yeah, something's happening. Okay, yeah.
Something
Just wait for the, I think, Subrat, you see this fine, right?
Yeah, we can keep it.
Yeah, we gotta wait for the projector to wake up here, but. All right. So the situation I'm going to describe is going to be like a model of AdS 3 CFT2. So the idea is we start with the tiling of the hyperbolic plane, which you should think of as a Cauchy surface of AdS 3, right? T equals 0 slice. And we tile it by pentagons. So the blue pentagons here are the tiling. And then we can have some fun with
Okay, pretty fancy graphic.
yeah, this is one of the things that my collaborators figured out how to do. Okay, so this is the tiling. So there's a bunch of blue pentagons.
Is it AdS2 tile?
Yeah, it's a tiling of H2 of the hyperbolic plane. This is a Euclidean time. This is a time slice of AdS 3. So it's just the Poincare radius. Yeah, this is a good tiling. And then the idea is that to build a tensor network, we're going to stick a tensor in the center of each of the pentagons. So now we can have some more fun. dots are going to be the tensors of our network. And
These were at the center of the original.
these were at the center of the original tiling. Yeah.
It's like the dual lattice.
Yeah, that's right. It's the dual lattice. Yeah. So then you see each tensor has 5 legs. So then the idea is going to be that for each of these blue dots, I stick one of these encoding tensors for the 5-qubit code. The 5 outgoing legs of the encoding tensor I contract with the neighbors. And then the 6th one, the input for the code, I leave free.
Okay.
So there's a J in the center of each of these blue dots.
Okay.
And then at the end, I'm going to cut off the network at some large but finite radius. And then the eyes are going to be the outgoing legs at the edge. So we've got a map from an index on from a blue. Each blue index has 1 qubit. So that's like a bulk field at each point in the graph. And then this gives a tensor which feeds that out into a state of the boundary Hilbert space.
Can I ask a question?
Yeah.
I mean, I can do this very abstractly. No need to draw on disk or. I store this in a computer. How do you sort of arrive at this type of a geometry?
Well, I think I've defined it. I just have to give you a good tiling. And then I say that in the center of each you have a tensor.
That's why this that earlier defining as coordination numbers. So there's no metric really. So drawing it metrically H2 is an interpretation.
Yes.
Yeah, sure, that's true. But right. But
there's an input there. It just
no, but the state. No, but I mean the graph has a geometry, right? Because the graph there's a graph metric. So right. So given 2 vertices, there's the number of the shortest number of links that you need to connect the 2. Right? And so that geometry is kind of consistent with this geometry.
there is a geometry.
Yeah, there is a geometry.
Some sort of discrete geometry.
Yeah, there's a discrete geometry.
Feels a bit like this p-adic kind of geometry that Upsal did.
That's right. Yeah. Although, well, okay, yeah. Right. So this is different than that though, because here there are loops. So in the p-adic tree there are no loops, and loops are very important for the error correcting properties. Okay.
You could have used Q-grids also, just an example.
Yeah, but actually the Q-traits turn out not to work because they don't have enough indices. So if I tried to do this with the Q-traits, I would have gotten the tree. I would have gotten the data lattice, and then it's not good enough to have a good code. So I did choose to do it this way on purpose. But yeah, it's certainly not unique. There are lots of things you could do. This is just probably the simplest one. Okay, so let me now draw this in a different way. So that's how I draw it. This is how my collaborator draws it, which helps to see the cutoff. Okay. So it's the same graph. So you see the pentagons now are the shaded white and gray, and then the red dots now are like the J indices, and then the white dots at the edge are the I indices. Okay. So this defines the tensor, which defines the code subspace, and you can check that because the tensors are perfect. This is isometric embedding. So the different, an orthonormal basis of the J's gets mapped to an orthonormal basis of the code subspace. So essentially, because the composition of 2 isometries is an isometry.
Where the J inner product is just red side by red side.
Yeah, that's right, side by side. Yes. So in particular, that means that the algebra of operators is preserved, right? So if you have an operator acting on one of the J indices, you can push it through the isometry defined by the network to define an operator on the boundary, and you have another one here, and they'll commute if they're not acting on the same site. So that's the setup. That defines the code subspace. All right, so now let's have some fun.
Just think
sure.
about the geometry.
Yeah.
So when we used to do this dynamically triangulated random surfaces in the matrix model days, so there one of the possible triangulations was to use the links to have the same lengths, and one played with the ordination numbers to have whether it's a positive curvature, local positive curvature or local.
Yeah, so here I don't want to do that. I want to hold the geometry like effective field theory in a fixed background. So the red dots are like what the matter fields are doing at each point in space. The reason, the back reaction, so I mean, we sort of, well, I was going to discuss this later, but right, we sort of coarse grained at the AdS scale. So at the AdS scale, there's kind of not much to gravity because the metric is gapped at the AdS scale. So there's not really much interesting, on further scales. The only thing you can do is make a big black hole, basically, which we'll see.
Something.
Sorry, can I have a basic question?
Yeah.
So this gives you a mapping from the boundary state to the code subspace. But what you're getting out of the rest of the really states, right? They're not operators. I'm confused about why they're localized.
Oh, okay. So right. So no, you said it backwards. So I think the right way to view this is that it's a map from the bulk Hilbert space to the boundary Hilbert onto a subspace of the boundary Hilbert space.
Okay, fine. Yes.
So if I have an isometric, so right, a unitary is a norm-preserving map from a Hilbert space to another one of the same dimensionality. An isometry is an inner product preserving map from a Hilbert space to another Hilbert space that may have a larger dimensionality. Okay. So this is an isometry from the 2 to the k dimensional bulk Hilbert space into the 2 to the n dimensional boundary Hilbert space. Okay. But now once I have such a map, I can also map operators from the bulk Hilbert space to the boundary Hilbert space by just conjugating them by the isometry, right? And the algebra of the operators will be preserved when I do that, for the same reason that the algebra is preserved for entire conjugation, right? Because they sort of cancel in the middle when you multiply the operators. So if I have from the point of view of the bulk Hilbert space, right? We just have a tensor product over the qubits on each of the red dots. So then in that Hilbert space, it's certainly true that a Pauli operator acting on one red dot commutes with the Pauli operator acting on another red dot. But of course, the algebra is not abelian, because if you have x and z on the same red dot and then you push them through, then you get non-commuting operators in the Hilbert space of the CFT.
So sorry, one thing that I'm not able to see in my head
Yeah.
in the proof that the perfect tensor nature results in the map from the J indices to the I indices being a unitary isometry,
Yeah.
and which is the following that, okay, I understand because it's a perfect tensor with equal, when I split it into 3 inputs and 3 outputs, it'll act like a unitary.
Yeah.
Now, these perfect tensors are contracted with each other, and I'll get a different unitary in the legs which are contracted, but somehow they must cancel out to result in a net unitary.
Yeah, so you have to realize that they have to cancel out to give you a net isometry, right?
A net isometry,
right.
yeah.
So the key point is that if you have a unitary transformation and then you move a leg from the input to the output, then you always get an isometry. So the way you should think about this is that we grow out sort of layer by layer. So I start with this guy in the center, and it has 1 input and 5 outputs. That's the way I want to think about it.
Okay.
And now, to get to the next layer, I just compose that with the product of 5 isometries. 1, 2, 3, 4, 5. Again, each of which has 1 input and 5 outputs. And then I keep going. And so, but at the next level, it can be more non-trivial. So, for example, this guy. So this tensor has 2 inputs and 3 outputs, but it's still an isometry. So each layer you're just composing more and more isometries, and then it's a theorem that if you compose 2 isometries, you get another isometry. All right. So that already gives us some bulk to boundary map, right? So if I have a bulk operator here, I feed it through the isometry, and I get some boundary operator that acts in the same way on the code subspace. And so that you can think of as being kind of like the global reconstruction, the first thing we talked about. It just gives you some representation of the bulk operator, not really worrying about where that representation is on the boundary. But of course, the real magic of this is that right, we want to do subregion duality. So we want to see that operators can be represented on a subregion of the boundary in a way like AdS can. So let's do that. So now I switch back to my picture. So say I have a bulk operator acting here. So in the center. Well, I guess probably the ICTS people can't see when I point, but I'm sorry, but hopefully it'll still be clear. So this blue box in the center is my right. So now, is acting on this dangling leg, the J leg of this perfect tensor. And then you see, the idea is now I'll pick these two black legs and I'll view those also as inputs. So this is some operator acting on these three. But then I can just push it to some operator acting on these three using this tensor pushing operation, operator pushing operation. But then once I've done that, I can keep going. So now I can take this piece up here and I can push it through those three, over to those three. And I can take this one here and push it to those three and so on. And keep going, and eventually I'm going to reconstruct some operator in the CFT which has support only on this sub-region of the boundary where the blue arrows are ending. And it's up to me how I do it, right? So I could have chosen to send this one down here instead, and then I would have gotten a representation over here. So you get this sort of redundancy where there are many different ways that you can push it, and you always get the same operator acting within the code subspace in the boundary theory, but with different support on the physical qubits.
So the operator you started with was acted with non-trivially in one of the two indices and trivially in the other.
Yeah, that's right.
And then you push that.
Yeah, and then each time, so now up here, right, now I say, okay, it's acting here, but now it's acting trivially on this index and on the dangling one, and so I can push again to the next three, and keep going. So notice also that things that are near the boundary, right, I can represent on a smaller region. So we get this connection I said about how well protected you are being related to the radial direction. Right, so things that are near the boundary are small, things that are near the center are big. And that was sort of the main thing that this has, which the 3Q-trade code doesn't have. Because now we have a sort of volume's worth of degrees of freedom in the bulk. Okay.
With a 3Q-trade, what you get more like a tree structure instead of.
Oh no, so I meant literally just the case where there's one bulk leg and three boundary legs.
Oh,
so then there's no network at all.
Yes.
Yeah, sure. Yeah. So yeah, this is an improvement on that, is what I meant. Yeah, because now we get a bunch of degrees of freedom in the bulk and a bunch in the boundary. So this is already pretty nice, I think. Right? Now we can see, this really gives a graphical illustration of how the locality in the radial direction is embedded into the Hilbert space of the boundary qubits at fixed time.
If your cutoff is after L steps of this graph,
Yeah.
what is the dimensionality?
Oh yeah, good. So you can compute the ratio. Let's see. I think the limit, as the limit as you take L to be large, is that K is equal to N divided by square root of 5. There's some 2x2 matrix you have to diagonalize to figure that out.
K is the code subspace.
Yeah, K is the code subspace. Yeah, so it has to be less, right? So it's a little less than 50%, roughly speaking.
So the whole thing is 2 to the power n. The
Yeah.
other thing is 2 to the power n over square root of 5.
Yeah, that's right. Yeah.
So,
And you had that formula yesterday, n is greater than equal to k plus 2l. That 2l was because we were doing this kind of very simple Q-trade model.
Yeah, the 2L. Yeah, so the 2L that was a sort of necessary but not sufficient condition. And there was some. Yeah. So that condition I think we should probably only think of as applying in the center.
In the center, but even
Or being sufficient in the center.
But even there's some variation of this, right? Is it that you protect against deviation again of roughly up to half of?
Yeah, and you can see that here too, right? Because you see, so I can represent this guy in the center on this blue thing here. So that means I can correct for the erasure of the complement of that, which is basically half.
I mean, does it always work? I can't do it in my head. Does it always work out to be half, or to the extent we trust the numbers, or is it 1 over root 5?
Oh, no, it's always a half.
It's always
Yeah, it's always a half. Yeah, because remember the inequality was n is greater than or equal to k plus 2l. And so the root 5 has to do with k. But here, like when you do that analysis, you think of k being order 1, so it doesn't matter. So it's just the half is just the erasure has to be half of it, less than half of the boundary. Okay. All right. So that's the code subspace. So of course now remember I told you the rest of the Hilbert space has to do with black holes. So now let's try to understand that.
You want to take a break, just in case?
Oh, I think this will be like 5 minutes.
Oh,
So
okay.
why don't we take a break after that? I think that would be a good stop. Okay. So here's the picture for how to think about black holes. So the idea is so consider this central tensor. Right? Currently, this central tensor has it has 2 possible input states, and it has 2 to the 5 output states. So that's the restriction, right? That's why the code subspace is small enough. So then we can get to a bigger subspace by just removing that tensor, and then viewing all 5 of these legs as inputs. Then that gives us a larger subspace, which contains the code subspace, but also contains some extra states, and then. And then there'll be a subspace of this Hilbert space where we just put the tensor back in. So then the idea is that the rest of those states should be interpreted as the microstates of a black hole, which is of 1 AdS radius in size. And you see that the physics of the exterior of the black hole is still working great here. So if I want to think about bulk fields here, I can push them this way, I can push them that way. As long as I don't try to go across this obstruction in the center, I'm still in good shape.
Can you just explain this again?
Yeah, so this is still describing a subspace of the Hilbert space, but it's a larger one because now there's 2 kinds of inputs. There's the blue dangling qubits on the remaining sort of bulk effective field theory legs, but now there are also the green inputs at the horizon of the black hole. And so now. That black hole generically is just going to be a black hole sitting there. But then if there's a particular set of microstates, which is where there's not actually a black hole, which is where I just put the tensor back. And that corresponds to having the vacuum maybe with some excitation there, but then the rest of the states are outside of the original code subspace. And so I want to interpret them as corresponding to the states where there's a black hole of 1 AdS radius in size. And consistent with that interpretation, we see that we can still reconstruct all the bulk outside of the black hole at all of this subregions and so on goes through as before.
And if you take the black hole to be arbitrary large, you get all the states.
Right, yeah, that is the point. Yeah, so now we can get a bigger black hole by now removing the next layer of tensors, and now we get more inputs. And we still got everything working outside, and now we've got more of the states. Indeed, as we keep going, we eventually account for the entire Hilbert space of the theory this way. So I claim this is a full model of the duality, with the full isomorphism of the Hilbert spaces.
So just to get this
Of the bulk Hilbert space, including black holes, and the boundary Hilbert space, including all the states. Yeah.
So if you took the
Sorry, one sec. Spento was asking something. Subrat.
yeah. So if you take the previous diagram that you
Yeah.
captured
Yeah.
and simply sort of cut out the region,
Yeah.
are you calling that a black?
Yeah, that's what I'm calling a black hole. Yeah. That's right. Yeah.
This diagram suggests the degrees of freedom that make up the states of the black hole live at its horizon.
That's correct.
Are you taking that seriously?
Yes. Yeah. Yeah. So yes, and you can check that the coefficient is consistent with the coefficient that appears in the Ricard-Kennedy formula. Yeah. Okay. Shiva, yes.
Yeah. The set of states that's represented by the tensor networking we discussed is a set of measures 0 on the boundary, right?
What?
The set of states that you can represent by
by removing tensors, the subspace gets bigger and bigger. And so in a limit where I remove all of the bulk tensors, then we've just got sort of the infinite energy black hole, or the black hole whose energy is aborted the cutoff, right? And now you've got the full Hilbert space.
Instead of thinking of set of measure zero, I think it's nicer to think of the dimensionality of the two.
Yeah, that's right. I think that's much better. Yeah, you should think about it as just, we're sort of decreasing the codimension as you remove more tensors.
We could have removed that region and tiled the remaining part as you did for the case where there wasn't a black hole. Why did you do that?
Sorry, why didn't I do what exactly?
You could have tiled this the way in which you tiled.
Oh, you mean like connected some of these together or something?
Yeah, I mean simply take out the region in between.
Yeah.
And tile the rest like you tiled.
Yeah, that is what I'm doing. Yeah. So all of the black lines here are still contractions. So the space out here is all still the same, and there are still fields that can be excited or not outside of the black hole.
But you need those white or green dots.
I need the green dots to get it right to account for the microstate of the black hole in the center.
He was saying that if you do a USA, just tile the whole thing, that was his previous one.
Yeah.
That was just the usual one, without it.
Yeah.
That's a very particular case of the black hole.
Yeah. This is a very special microstate where actually there's no black hole.
So the growth of this, right now, this black hole has 2 to the power 5 microstates.
Yeah, that's right.
And then if you take the thing to the next layer, you will probably have some 2 to the power
15 or something.
like
Yeah, there's
that.
some formula.
So is that growth the same as the
That's right.
what should happen in the?
Yeah, I mean, it's fairly clear it's going to because the geometry is the same, right? So, of course, I'm not trying to match the coefficient in the Bekenstein-Hawking formula, right? So if we're not going to insist on matching that, then this is clearly going to work because, just because it's the same physics that we draw. Like if you look at what the AdS Schwarzschild geometry does, it's precisely this. It removes a region in the center, which is the order, the size of the Schwarzschild radius, and then away from that is just ordinary AdS. So up to the order 1 factors. So the only sort of right. But of course you can get a little bit confused about the fact that the volume and the area are kind of the same.
Yeah,
right? So then you also have to look at the scaling, right? So basically the entropy of this is sort of multiplied by the log of the range of these indices. Right. And so then you have to. So one way to normalize that is to observe that even in a vacuum, if you look at the entropy of a subregion, so this I haven't talked about yet, but this obeys a version of the Ruth-Hakinagi formula. So you find the sort of geodesic and you see how many legs are cut, and then there's some multiplying factor that gives you the entropy. And so right, so then somehow that factor should be the same thing appearing in the black hole entropy factor. It is.
Are you going to do the Ruth-Hakinagi formula for us from here, or is it obvious? Just because you haven't set it in the.
No, it's not. It's not obvious from here. The most of this lecture after this is going to be about the Ruth-Hakinagi.
Okay, fine, right.
So
because it was
yeah, so it shouldn't be obvious.
Just confusing me with the factor of n. So in both the black hole and the Ruth-Hakinagi formula, you need a factor of n squared. So are these tiling supposed to be 1 tiling per Planck length or per Planck area?
Oh no. This is per area. So here in the code as I presented it, n is order 1. So you can't really tell. So the way you should think about n is it's the range of these indices. So to get something where you can really clearly separate the n scaling, you need perfect tensors where there's an order 1 number of output legs, but the range of the indices is large. But so these are supposed to exist. I'm not sure I can pull one out for you off the top of my head. But then once you have that, then you can talk about the n scaling. I should also add, though, that I think there's an even better answer to that question, which is that the group at Stanford pointed out that if you replace the perfect tensors by random tensors, and then you just average over the tensors, then everything works beautifully. So it works beautifully, but approximately. So in the limit that the range of the indices is large, you can compute everything analytically, and you can see that indeed the sort of n-scaling here is the same n-scaling from the black hole. For the Ritakinagi and the black hole are the same.
What do you mean random? You get superposition of states then.
No. Random means you. Okay, so the perfect tensors, their hallmark is that if it's a bipartition, you get a unitary, right? So the idea is that you just view it as a map, say from 3 to 3, but for when the index range is large, and then just pick a random unitary from the Hilbert space of 3, qubits to the Hilbert space of 3 qubits. And then the key thing though. So the reason actually, so we thought about it in our paper, but the reason why we didn't do it is because for everything to work, you have to allow yourself to choose the tensor independently, randomly in each respect. So if you try to pick the same tensor once and for all, it doesn't work. So you have to sort of each time pick a different tensor, and then statistically the symmetry should be restored.
And you have to decide which are your 3 and 3.
Yeah. No, yeah, but it doesn't matter though in the end. Yeah. I mean, you have to pick, but in the large end limit, that's a subleading issue. Yeah, and that also helps with the derivation of the Ritakinagi formula. So here the Ritakinagi formula is sort of almost true. So because of the discrete nature of the graph, depending on precisely which regions you pick, you can kind of miss by a little bit because you get stuck on some discrete artifact of the lattice. And so the random tensors fix that for you. Yeah.
Did you discuss the Ritakinagi formula yet?
No, I assume you've all heard of it though, so I just mentioned.
No, I'm sorry.
Yeah.
Very ignorant.
And is it interesting to try to understand what kind of dynamics would give rise to such a ground state?
Yeah, it is. So, I mean, yeah, let me think about that. So of course, right. So, well, yeah, actually, let me see. I think I wrote some comments about this. So let me see what I said. Yeah. Okay. Good. So okay. Let me now summarize this before the break, and I'll make a comment about that. So the good news now is that we have radial locality, we have subregion duality, and the black hole entropy seems to be working more or less as you want, all in an exactly soluble context, which is pretty nice. But of course, this is not the full story, right? So the two glaring things which this model does not have are locality below the AdS radius and dynamics. Now, it doesn't completely not have dynamics because we've chosen this subspace to be special, roughly speaking, because we think it corresponds to the conformal image of low energy states in the CFT. So we're putting in some kind of information about the Hamiltonian when we do that. But we haven't distinguished one low energy state from another, right? So you're either in or you're out. And, which state you feed into these dangling legs that is actually the ground state is something that we haven't said. Right, so then you don't have time evolution, that's right. So this is a kind of picture of the duality at fixed time, right? So you kind of, you have some, Wheeler-DeWitt patch or something, and you're sort of constructing things in here at fixed time.
But I do energy minimization at fixed time. That concept exists.
But to do that, you need to know a Hamiltonian.
Yes.
Right? So,
we don't have one yet.
Yeah, currently I don't have a Hamiltonian. I said I think these states are low energy. And then I think the ones with the black hole get higher and higher energy. Right? And but I didn't give you the Hamiltonian. I can of course just say, I can declare that to be true, but it's not that satisfying, right? So, and I don't a priori know if so we could just pick some Hamiltonian on the boundary, right? We could, do the transverse field Isaac model or something,
right,
and then see what happens with these states.
I
haven't done that. I mean,
whether these states are special in any way.
Yeah, that's right. I mean, I think they would. I think if you did that, then they would be sort of lower energy than the other states in the Hilbert space. But how would you actually get the ground state? How would it? I mean, not
So
totally.
the original network lattice that you chose perhaps has something to do with the Hamiltonian whose ground
Yes.
state you're trying to.
That's right. Yeah. So I implicitly put in information about the Hamiltonian by saying that I think this subspace is a model of the low energy states in the CFT.
What would be really cool would be to have some sort of integrable system with a Bethe ansatz that gives you the solution.
Yeah, that would be a lot of fun. But I mean, it's not, you have to, I haven't just given you the ground state, I've given you a whole subspace with no preferred member. So what you would want to show is just that the ground state is somewhere in
dispersion
there.
relation.
Yeah. So I mean, the natural guess for what the ground state would be, I mean, so very naively you might think you should just feed in a product state into these red dots, but that can't really be correct.
Because it's uncorrelated.
Yeah, that's right. Right. So what you should really do is you should feed in a short range, sort of a massive, the ground state of a massive theory, right? Because it's gap at the AdS scale. Right? So you want the bulk correlation to fall off exponentially with the graph distance here.
You want a discretized version of the vacuum for a massive field.
Right. So it would be fun if you could find some boundary local Hamiltonian like the transverse Ising model, and then see that the ground state of that indeed has this kind of gapped fall off in the bulk. But no one has done that.
Sorry, one more question. Every example of best understood examples of AdS CFT make crucial use of gauge invariance.
Yeah.
I don't see any sign of that here.
Yeah. Well, I think there's a lesson you should learn from that, which is that gauge symmetry is superfluous. As we already know, gauge symmetry is superfluous.
I know, but it was sort of in AdS CFT, having, for instance, in n equals y angles, the fact that you've got these low energy states make use of these single trace operators. That you have a spectrum at low energies that's independent of n, and then the spectrum at high energies knows about n. Gauge invariance, at least in that example, are very important.
Yeah, no, right. So gauge invariance is one way of getting holographic CFTs. But nobody has really given a good argument that's the only way. In fact, I think you can almost, so say I just come to you with a CFT.
Yes.
And I'm, say I'm a bootstrapper. So the way I do it is I hand you a list of operators and a list of OP coefficients.
Right.
Are you going to tell me whether it's a gauge theory or not? Do you think that makes sense?
No, I probably can't.
I think you probably can't, right?
I think I probably can't. But if you want to write down local Hamilton, local Lagrangian on the boundary, then you might start wanting to know what this is.
Yeah, but that's not even preserved under duality, right? So I mean,
Okay.
Well, we're going to discuss this in my colloquium this afternoon, but I think So do you think V1 V5 is a gauge theory?
Some sense.
Wait, isn't it? Can't we used to say it's the sigma model and the moduli space?
I agree.
Yeah.
I agree. But it preserves this discrete gauge symmetry, which is the origin of twisted sectors.
Yeah.
Which does the same thing, which gives you this low energy sector.
Well, isn't that just some quotient of the target space?
You can say it anyway. Okay, I'm just saying that if you let me make my comment here.
Yeah.
If you wanted to make a model system that had a good chance of getting something like this, AdS, you might want to start with something with gauge.
Well, good. So let me make one other comment about that. So I think you're going to be more correct with that statement if you're trying to get locality at sub-AdS scales. Because locality at sub-AdS scales is all about what's going on inside of the n by n matrices. And then the fact that you're sort of interested in singlets and so on has to do with that. But here we're not doing something so fancy as that, right? We've only got locality at the AdS scale. And so I guess that this presentation in terms of a gauge theory and so on is less.
Could you work this out for Mattich and Simon's theories, where we've got locality only at AdS scale? It's a very crude example, but it's sort of solvable.
So currently the only thing I know that does this is there's a paper by Joe Polchinski and Vladimir Rosenhaus and Eric Minton. So they did an even cruder thing, which is they did a free scalar in 1+1 dimensions and then just projected onto singlets by a free ON scalar and just projected onto singlets by fiat. And they found that they were able to reproduce these kinds of things in that model. Now, there's a mistake in their paper, which is that they argued that the gauge symmetry was necessary for this to work in all cases. But the calculation is correct. And that's a case where you can sort of see explicitly, because it's free, that an operator here is equal to an operator there.
So you derive the operators of a CVF theory somehow.
That one is not even really Dildé-Vasiljev, right?
But in their example, if I remember right, please correct me, it wasn't, you were not doing this bulk reconstruction so much because of perfect tensors or something, right? But just due to the gauge invariance, right?
Yeah, but that was just, right, but the key thing is that they assume that the energy of the state is order 1, and the limit limit that n goes to infinity. And so that puts them in my code subspace. And then you can do the calculation in a way where it looks like gauge invariance is the thing that explains why an operator on one region is equal to an operator on the other region. But that calculation is only valid in the code subspace. And so the constraint, the mistake they had was they wanted to say that gauge constraints are enough to solve all of this puzzle with time slice axing and so on. But that's definitely not correct. If you're already in the code subspace, then of course you have to take into account the fact that it's a gauge theory when you're doing a calculation. But gauge theory is still, they're still basically local, right? So the free energy at sufficiently high temperature is still extensive. So you can still basically think of it as being local degrees of freedom in each point in space. And so this picture of what's going on is still more or less correct.
Just to understand, is it that what you got here through perfect tensors can be obtained instead by gauge invariance if you were in the code subspace? You're also saying only for code subspace states you get bulk reconstruction.
That's
you
right.
have perfect tensors.
But to be clear, I don't want to declare that perfect tensors is the new religion. I just used it in this model.
Right. I understand. But I was trying to ask whether instead gauge invariance could get you all of the way, most of the way. What is the...
So in that model, it seems to be the answer is yes. In this 1+1.
But more generally, has somebody thought of this?
It's very hard. You have to. If you want to, doing it that way, you have to be able to solve the continuum quantification.
But say take a three-dimensional scalar field with only the Gaussian. Okay. Take the lump that is 0 limit. Very simple.
You mean just do their thing in one higher dimension?
Do it so we know that this is a CDF dual.
That you might be able
That's
to
what
do.
it was. Okay, you can put in Chern-Simons.
Put in Chern-Simons, but to start with, take K to infinity.
Yeah, I was thinking even just put in the...
But you put in the Gaussian.
Put in the Gaussian.
That's what they did. I think probably, they did it, it's easier in 1+1 dimensions, but probably you could do it here also.
But could you produce, a bulk diagram like this in that theory? And argue that?
Yeah, I suspect so.
And argue that there's no energy excitation.
The bulk diagram, you would literally get a bulk diagram with some kind of tiling and so on, or...
No. This is, because it's, the non-locality is more, subtle in that than it is here, right? But here we've just sort of, spin blocked each AdS radius into a site. That's kind of what we did here. Vasilyev is doing something more sophisticated than that.
But before angle is a very weak coupling.
Yeah, you can also try that.
Not even include any interactions.
No, but just lambda goes to 0.
Correct. And then see whether gauge invariance gets you all the way.
But what does that even mean?
Well, what I thought was, I'm not sure, it was what Daniel showed very nicely, beautifully in this example, is that he gets his bulk reconstruction property to come out.
Yeah, so the calculation you do is you, so you take the formulas we had in the first 2 lectures, right? So there's this smearing function representation of this, right? And then you use the fact that since the boundary theory is free, you can, normally these operators are non-local in time, but you can just use the free equation to just evolve everything back to t equals 0, and it stays linear in the operator, right? So, and then once you have that, now since everything is represented at fixed time, there aren't any secrets, right? So you can just take a representation, say here, and a representation, say here, and compute the difference and ask if it's 0. And it better be 0 if this representation bulk is correct.
In your code subspace.
Yeah, in the code subspace.
You have to understand what your code subspace.
Yeah. So, but the way you do that is you just restrict the states where the energy is of order 1.
Right.
So, and then that automatically puts you in the code subspace. And so these are going to have to be, the difference does have to be 0 if there's a bulk. And it is, and so, if there's a way of presenting the calculation where it looks like the difference of the 2 operators is something which is 0 because of gauge invariance.
Wait a minute, either the 2 operators are gauge equivalent or they're not, right? Or in the action of gauge invariance.
No, because we're in the subspace, right? On the full Hilbert space, they're not equivalent.
In the code
Okay.
subspace.
On the full Hilbert space, they're certainly not equivalent. That was the mistake of Polchinski. Even in the gauge theory, an operator here is not equal to an operator there acting on the Hilbert space of gauge invariant states. But you can ask in a code subspace if it's true. So one way to arrange that calculation is by taking the
Is
large
it-
n limit first.
You see, it's just not true that those the two operators in their paper acted the same way on all gauges.
That's correct. It's just not true.
So it's an algebraic mistake.
Well, no, there's not an algebra mistake because they took the large n limit. So they're implicitly working in the Hilbert space of states of finite energy. But had they worked at finite n, then the terms they neglected, they wouldn't have been able to neglect, and the operators wouldn't have been equal, and there would have been no way to fix it.
I see. But
So you might say gauge, I could imagine trying to argue that gauge invariance was necessary if you could get over this point that gauge invariance doesn't mean anything, but you're certainly not going to be able to argue it's sufficient without going to a subspace.
But anyway, we want to argue in a subspace, right? That is, we want to argue that only for special states in a subspace you have boundary construction.
Yeah, sure, but right. But the whole point of the story is that the states which you don't want it to be true, it's because there's back reaction to the bulk. You know, the states where it's not true are physical states. That's the difference, right? So I mean, they would, in their proposal, they would have said the states where these operators aren't equal are unphysical states that even if finite n.
No, I understand, but what I'm saying is, if you work at finite but large n,
Yeah.
then this boundary construction will be a property of some code subspace.
Yeah.
But you'll have other states,
Yeah.
which will be the analog of your black holes,
Yeah, these guys.
for which it won't be true, but they'll be there in the gauge theory as well.
Yeah, they'll also be there in
And-
gauge theory.
and,
That's right.
I'm just wondering whether the gauge constraints are good enough to reproduce some of your nice properties.
Yeah, so I think if you stay out of the black holes, then at least in this one example, it is. Yeah, and it might be that you could generalize what they did to some free n equals 4 or infinite
worth
k
trying.
Simons matter. I don't know.
But just okay. Do you think that there is some analysis of one of these nearly free theories that give rise to such a diagram?
Oh,
I mean, I like
this one?
this
or-
diagram. Yeah, something reminiscent of this diagram. I'd like to see this diagram coming out of dynamics, not just declared.
I'm missing some.
Well, to have this diagram, you have to go to finite n.
So, but I've got this almost free theory at large but finite.
Yeah, but then you have to consider states whose energy
No,
is
let's go to
order,
the previous diagram first.
Oh, okay.
The Gauss law constraint.
Yeah, I'm satisfied at the moment with this diagram.
Yeah, I think that's basically what Polchinski and Rosenthal did.
But what was the analog of this tensor network?
Oh, no. You just get the subregion duality. I mean, the tensor network is just a toy model for generating the subregion duality and so
So
on.
that's what I was trying to understand. Do you think that the tensor network is a real physical fact about AdS CFT, or it's just
Oh, no, absolutely not. Yes. No, right. I mean, there are people who have this fantasy that by taking the continuum limit of tensor network, you can generate actual quantum gravity. That's not how I think about it.
so you're just thinking of this as one toy example?
Yeah, this is a toy example, right? But it's
But there are other
it's
toy
nice
examples.
because it represents sort of the essence of how it works graphically.
All that you want is the subregion duality and Butak-Tanagi.
Yeah, that's right.
And any example that gives it, you're happy with, this
That's
is
right.
one that will.
That's correct. Yeah. This is like the simple harmonic oscillator or something. It's not. I don't think everything is.
I understand.
Also, perhaps what Shiraz is saying is how will then Ryu-Takanagi and so on, which kind of works out geometrically or graphically in your model.
Yeah.
Why will that work, right?
Well, no, I think this is a caricature of what always happens at the NES scale, but it's a cartoon, right? I mean, it's not what actually happens. It's kind of the skeleton of what happens.
You won't get some things right.
So sorry to go on. And I mean, one of the things that's really interesting is a way of reconstructing the bulk from the field.
Yeah.
And you have this diagram that sounds like if you had a principle to generate it, would more or less reconstruct the bulk from the field.
Yeah.
And I was wondering whether you could just implement, whether there was a clear principle and whether you could implement that in a simple toy example, like a almost free theory. I mean, that would be really fascinating, right? If you could have an algorithm for generating the bulk picture.
Well, so of course the HKLL kind of already does that in actual holographic CFTs, right? The only annoying aspect of it is that you have to do this time evolution of CFT if you want to express everything in fixed time, and that's hard.
You have to know the bulk evolution. I'd like to start just with
No, but say if you start with n equals 4, then supergravity is unique, so you know the bulk equation of motion.
You know at a very large number.
Yeah,
But suppose you wanted to do the same at small
integrability.
at all numbers.
Oh.
I just want to
But
feel that.
well, okay. I mean, you could derive, I think you could derive this kind of picture where you have stuff here and it has representation there and so on, but probably you would use HKL if you actually wanted to write the formula.
Okay.
Yeah, I don't think this suggests a way of actually writing the formula
Okay.
for continuum CFTs.
Okay. Thank you.
Yeah, no, I think it's just a
That's all.
it's a toy model. All right, well, maybe we should now do the break.
What did he say?
Questions?
Yeah.
Time.
Very basic actually. When you explain this thing of pushing the bulk operator to get the, to the corresponding weld on the boundary,
Yeah.
the bulk, I thought you can push operators to perfect tensors if they act on 3 of the legs, or right?
Yeah, on three or fewer, because I can always, so say it acts on one, then I can just say it's the identity acting on the other two.
I see. Okay. Okay. So that's how you push the operator by making the identity acting on the 2 legs that are.
That's right.
Okay. But then there's something else that confuses me, which is that you don't have to push it all the way to the boundary. You only need to push it some part to the boundary.
Well, I could choose to do that, yes, but if I want to get a representation that's explicitly in terms of the boundary qubits, then I have to push it all the way.
Correct. But you could also choose not to push it all the way to the boundary.
Yeah, that's right.
And what does that mean? That says that a bulk operator can be written as a combination of other bulk operators, or
No, it doesn't. It doesn't mean that because what?
Because of dangling legs.
Yeah, it's because the operator is not just acting on the dangling legs; it's acting on the contracted legs.
Good.
So
What is that? But is there an actual interpretation of that, of the statement that you can have a bulk operator written in terms of other complicated operators that are,
oh, you're asking about like bulk Riesleiter?
this is not really bulk Riesleiter, right? This is really saying an operator in the bulk is equal to another operator in the bulk.
No, but it's not saying that. Now, operators in the bulk are operators that act on the J, on the red dots, right?
Right.
But when you're halfway through pushing, that's not what you have. You have an operator that acts on the contracted legs.
It's like, I think it's like RG flows. If you bring the boundary in, that's the kind of thing you're talking about.
Yeah.
That's right.
Yeah, you can certainly bring in the cutoff, right? Yeah, then it's RG flow of the operator. That's right.
Yeah, no, I understand that. I'm only asking what is the interpretation of these operators that act in some of the legs in the both subspace and some internal legs, and are localized somewhere in the middle.
Yeah, I don't know. I mean, I guess what Strauss said about the RG flow is probably the best I could come up with.
So what was the question? Sorry.
He was just asking about if you push halfway or something.
Oh, if you push halfway.
Yeah, then what do you think about that?
So it's not quite a local operator because you pushed halfway.
Well,
But it's not spread out all
it's
the
not
way to
really
the
an
boundary.
operator either on the boundary or in the bulk.
It's got these cut legs.
It's got these legs in the middle. That,
Yeah.
It's somehow acting in the middle of the network.
Yeah.
So it doesn't have an interpretation just either in the bulk or the boundary fluid space.
Right.
All right.
So Rad, I don't think you should think of it as acting partly on the bulk and partly on the boundary. It just acts on a higher cutoff boundary or a lower cutoff boundary.
Yeah. Or boundary, you mean?
Yes.
Cut off boundary. Yeah.
Because it just goes all the way to the edges of that new boundary.
Yeah, that's right. All right. So shall we now move to Ritakunagi? Okay. So now RT and okay. So this will seem like a different subject for a while, but then hopefully, at some point today maybe or maybe tomorrow, we'll see it come back together and be related to what we've been doing so far. Sorry, Thursday.
I mean, if it's okay, we'll meet on Thursday.
Yeah, sorry, I meant Thursday. Okay. So what is this Ritakunagi on? So Ritakunagi says the following thing. So say that we're given one of these spatial subregions A at a fixed time in the boundary theory. So we could then imagine computing some state in the CFT, the von Neumann entropy of the reduced state just on the region A. And what Ryu-Takanagi, so let's first give the initial version of the formula. And we'll see as we go on, we have to keep refining the formula. So this will be the first attempt at the Ryu-Takanagi formula. That it's the area of some surface, gamma A in the bulk, divided by 4G, where gamma A has extremal area. So the variation of the area under variations of the surface is quadratic. The boundary of gamma A equals the boundary of A. So that means that that since A is codimension 1 in the boundary, this surface is going to be codimension 2 in the bulk, right? Because their boundaries have the same dimension, but this one is living in one higher dimension. So for the AdS3 I've drawn here, it's some surface like that, gamma A. And actually, so here it'll just be a geodesic for AdS3. We need that gamma A is homologous to A. So don't worry about that too much for now, but what this means is that there exists an achronal surface. I'll call it I think this is capital C. Is that right? Capital Chi? Capital Chi? Yeah. But one of those is an X.
What like the smaller Greek letters are they?
I know, but surfaces to me have to be capital Greek letters. You know, I've spent too much time reading the Hawking analysis.
What is that word? There exists an
achronal surface. So that means every point on the surface is space-like separated from every other point on the surface. Such that the boundary of chi A is equal to gamma A union A. So here's chi of A here. Let me shade it in. Really not good for shading. This is chi A here. So that's a restriction on gamma A. Not all gamma A's necessarily have such a chi A, so that's what this homology constraint is saying.
So gamma is homologous to A.
Yeah, so you see here I can deform it to A, roughly speaking. But it's not, so I didn't say homotopic though, which is what that would be. It's homologous, which is this.
There exists an equivalence of the sigma A such that the boundary of sigma A is gamma A.
So gamma A can be taken to A without encountering a black hole in the middle.
So that's how it's usually used, yeah. So there's not some kind of obstruction here preventing gamma A from reaching A. This won't matter for most of what we're doing. I mostly just mentioned it to define this chi A because I'm going to use whatever Ca. I would call it sigma A, but I'm using that for the boundary quotient surface. Okay, so let's call it chi A. So this is okay. So this is the original version of the Ryu-Takanagi. Okay. Now, the first refinement, which will be enough for us to discuss for now, says that well, S of rho A is equal to the trace of rho times some operator LA plus what I'll call S of rho chi A, where now LA is a quantum operator, which is the area of the extremal surface operator divided by 4G plus higher order corrections that are integrated over the surface gamma A. So L here stands for local. It's localized on the surface gamma A. And then this is the bulk state on this aquanal surface. So this is what Bekenstein called, it's kind of reminiscent of what Bekenstein called the generalized entropy, right? So it's saying that the entropy is the area plus the entropy of the stuff outside. Right? So that's what this term is here. And then there's a whole industry of people studying these corrections. So I guess currently Shidong has the record for computing the most terms in this expansion.
I mean, that's to begin with just the one root determinant or something, right?
Well, yeah. So if you think about computing this in Euclidean signature, then the one determinant enters into the calculation. Yes. But this is kind of a Lorentzian formula, so the split doesn't quite work in that way. And so this and then this I would say was first sort of really argued for in a good way by FLM, which is Faulkner liquids and all the same. And indeed, both of these. So this version of the formula was first conjectured by Ru Takenagi. The version I presented here is called HRT. So it's Hubei, Rangamani, and Takenagi. So it's always confusing who the R is when we're talking about these things. There's Ru and there's Rangamani.
What is the first of that tree? So LA. LA is supposed to be an operator.
Yeah, it's an operator. It's the area of the extremal surface operator plus corrections. So yeah. We're interpreting this as an expectation value, right? So because this is a formula that should be true in a quantum state. So this isn't really well defined, right? Because the area of the extremal surface is an operator. Remember, we're always doing bulk quantum mechanics. So.
Then we get into the question of, okay, how do you define an area operator? I mean, are we trying to do it precisely in quantum gravity?
We do it perturbatively order by order in 1/g. It's the same story as we've been doing all along.
So then, just to understand, at least to leading order, there's just a classical surface, and then how do you correct it in 1/n?
No, but you might have superposition, right? I mean, so, as you go to higher orders in G, the metric is fluctuating, and, you're clearly going to have to talk about an operator.
It's not well defined anyway, this perturbation theory. In quantum gravity or computing this?
No, but it's defined as an effective field theory. So this is the same thing we discussed in the first lecture. You have an effective field theory with a cutoff. There's a sequence of higher order terms which are fixed by matching to string theory. And those higher order terms go in here into these corrections.
One way of defining it, consider the path integral of gravity. For any given metric, there's an extremal surface.
Yeah, that's what I was going to say, yeah. So the right way to think about this is the area of the extremal surface is a functional on the phase space of general relativity. So in quantum mechanics, it's a linear operator. It's a complicated linear operator, but who cares?
I mean, string corrections are fine, all right, you have some R squared term and you've got a saddle point and I include the effects of the R squared.
No, but
What does it mean to have the 1/n corrections?
Just think, if you think of the path integral, right? You have a gravitational path integral. This is a gauge invariant operator you can insert into the path integral as many times as you want.
Given a bulk metric, you're integrating over bulk metric. For any given bulk metric, given the boundary region, there is an extremal surface.
That's right.
And then you weight the bulk integral by that.
That's right. Yeah. That defines the operator.
I mean, it's form.
Most metrics are not different.
Or what?
You're going to extremize, okay, no.
I mean,
Most metrics are not continuous. I don't know.
Come on. Whenever you write down a path integral, you're allowed to put in a function of the.
This is semi-classically, it's good what you're doing.
Yeah, I think to all orders in perturbation theory, it's clearly going to be fine.
That's so.
But it's just, sorry, I mean, the Ryu Takenagi formula I thought came because we did a replica trick path integral and it got dominated by a saddle point, right?
That's what I call the initial version. This is the quantum version, which extends that calculation to higher order. So far, I should be clear. So far,
you just do the replica trick path integral and you get what you get, I would say. I mean, what is the...
No, you have to put in a stage. Well, I was about to, so we haven't yet discussed how this is derived. I was about to mention that. So
I mean, I I can understand that the generalization is the replica trick path integral. Fine, but when you break it up like that and so on, I'm not sure.
No, so that's what's done in FLM, right? So what is done in FLM is you take a state rho, which you prepare by some bulk path integral involving sources. Okay, and that state may have superposition of a planet, not a planet. It could be in general some complicated state, some state of this perturbative effective field theory, including a metric, and then you do the replicate trick, but you compute through order G Newton to the 0 instead of, right? So if you compute to order 1 over G Newton, that's what Lukowitz and Modosena did, and you get this. But then if you go to the next order, then you get this. And the fact, and the way you see that indeed there's an operator there is that at order G to the 0, the saddle point, the area of the saddle point, I should say this way, the area of the saddle point can change at order G to the 0 because of metric fluctuations. We have to keep track of that. So, and you see that it goes into this term. So yeah, I would suggest looking at this if you're suspicious of that. I didn't want to make this a lecture about Lukowitz and Modosena because that would have been another lecture by itself. So I guess it's better if I just ask you to accept it.
Yeah, fine, but sorry.
Yeah. I mean, the logic is indeed you do the replicate trick.
Does it work at G squared?
What?
Does it work at G power plus 2?
What?
Does it work at order G power plus 2?
No. So at higher orders in G, there's a conjecture for what the formula is, which is due to Engelhardt and law. So at higher orders, you need to deal with the fact that the surface itself also moves, which you didn't have to deal with at order G to the 0. So then the proposal is that you extremize the sum of these two terms to find the surface. And there is, I believe, a proof of that in the work by Shi and Aitor, but it's unpublished currently, which extends it to all orders of G. But for the rest of this talk, though, and for the rest of the week, I'm just going to work in order G to the 0 so that we don't have to worry about the moving of the surface. Okay. All right, so we're happy with the RT formula? Modulo the fact that I didn't show you the derivation structure. Okay. So now what I want to emphasize, though, is that from the point of view of the causal wedge reconstruction, which we've discussed so far, this formula is kind of surprising. And the reason is that, in general, gamma A, the extremal surface, is not contained in the causal wedge of A. It's not obvious that it should be in the causal wedge of A, certainly. And it's not that hard to come up with examples where it's not, and I'll present a few in a minute. So that seems to suggest that this subregion duality based on solving bulk equations that we've been discussing so far has to be incomplete. Because apparently we can learn the area of the surface by computing the reduced density matrix of just the degrees of freedom living in A. So those degrees of freedom living in A must know something about what's going on in the vicinity of this extremal surface, even though it's not in the causal wedge. So that's good. It means that there's something more for us to understand. There's more to life than solving the bulk PDE. Now, we can think about what would be the best thing that we could ask for. So now that we know that we can go beyond the causal wedge, how far can we go? What would this suggest could be sort of the farthest at which we could go? So let me make a definition. So the entanglement wedge of A is W of is chi sub A. So in this, so that means in the bulk now, right here's chi sub A. So its domain of dependence is like the bulk causal diamond sitting on top of chi. And so you see that's also going to kind of look like a wedge. It's going to look similar to the causal wedge in terms of the shape. You know, there will be some rim and then it'll go out and intersect the boundary somewhere.
Anything with time independent situations?
No, I'm not restricting to that. I'm discussing arbitrary.
This chi sub A was supposed to be space-like?
As achronal, but it's not unique. You can move it around however you want. It's not going to change.
And what was achronal like about this?
Achronal means every point on it is space-like separated from every other point.
Okay.
Sorry, so you take sigma of A and then what was
The bulk
you say?
causal wedge.
I take the bulk causal diamond.
But causal, just to understand causal diamond, you mean all points which
Yeah.
receive light from A as well as
No, yeah. So the causal diamond is the set of all points. How should I say this? Right. The right way of saying it is it's the set of all points where if you have a causal curve going through that point which is inextendable, then it has to intersect this region. That's what a relativist would say.
okay. So take all the points such that if you extend backwards or forwards in time, what kind of a curve again? Causal curve.
Yeah, causal just means not space-like. I can also say time-like. I don't care about whether the boundaries are included or not. So yeah, maybe a more intuitive way to say it is if I give you Cauchy data that lives just on this chi, it's the region where the solution of the wave equation is uniquely specified.
Thank you.
So it can't. So you're right. It can't receive signals from the complement of this. Yeah.
Okay. Okay, very good.
It can't send or receive signals from the complement of this. That's the best way of saying it.
Maybe able to send.
No, so it's like this, right? So down here is a point which can, right. So if this point it obviously can't receive a signal from this.
I see.
Right, from this, but it can send a signal to this. So therefore it should be included. All right. So now there's a very important theorem central to this whole business, which is due originally to Aaron Wald, and then sort of refined by Hedrick, Hugani, Lawrence, and Ragamani, which says that C of A is contained in W of A. So the causal wedge always lies inside of this entanglement wedge.
Causal wedge of A,
Yeah.
which is
Shall we remember? So let's remember the definition of the causal wedge.
so the bulk
Was the intersection of the bulk future of the boundary domain of dependence of A with the bulk past of the boundary domain of dependence of A. So there the idea was we took A, we built the boundary causal diamond, and we took the intersection of the future and the past. So they both make this kind of wedge kind of region, but the entanglement wedge can generically is bigger, and it's never smaller.
Right. So the causal wedge was the set of points in the bulk which can both receive light from the boundary diamond
Yeah,
and send light to it.
that's right. Yeah.
Okay, and this one is okay, the entanglement. Okay, yeah, that's good.
So the reconstruction theorem shouldn't apply to W of A rather than
Right.
C of A.
Exactly. So then the obvious guess for how to account for this mystery with the RT formula, knowing more than the causal wedge. So it suggests that the best thing that we could have is just that in fact everything in the entanglement wedge is reconstructible. Okay, so that's called entanglement wedge reconstruction conjecture. That everything in the entanglement wedge can be reconstructed. And by the end of the lecture we're going to prove it, or by the end of the week at least. So, consider a few examples where we can see what in the end is the difference between C of A and W of A. So examples. Okay. So the simplest thing we can do is take A to be ball shaped in empty AdS. Alright, so that was where we did the AdS Spindler reconstruction before.
A to be ball-shaped, the region of the boundary.
Of the boundary and the bulk geometry to be pure AdS.
So ball shape meaning at constant time slice you take some.
Yeah, a round ball. Okay, and then so here it's an easy homework problem to see that W of A equals C of A. So there's nothing new to be learned about that situation. I'm actually not sure about if A is connected but not a ball shape. I was thinking about that last night. I realized I don't remember. That's actually.
Ball means literally with the standard metric
Yeah, the
of
round
boundary
ball.
and
Yeah.
the round ball, equidistant or whatever.
Yeah. Yeah, you take a circle. So for me, the boundary is always a round sphere. So then we take a round ball, sitting inside that. Okay.
So you mean if instead of a ball it was some other shaped object, it's not clear?
Yeah, it's not so clear that they're going to be the same. But let me give a sort of more fun example where they're not the same. So, and this is the sort of canonical example that everyone turns to whenever they think about this. So let's consider just AdS3 CFT2. And consider the case where A is a union of two disjoint intervals. So now, the causal wedge is going to be, we draw this, it's just going to be the union of the two causal wedges, right? And if you're solving, bulk PDEs with boundary conditions, you don't, if I give you the boundary conditions here, you don't care about the boundary conditions there, right? So you just ignore this, and then it's just the causal wedge of this guy, and then similar to this one, and then the union is like this. But now, when we find the entanglement wedge, there's a difference depending on whether these guys are big or small. Because, well, if they're small, then it's the same. So the minimal area surface is like this. Oh, that reminds me, I forgot to write a line in the definition of gamma A, which is that if there's more than one extremal surface, you take the one of the minimal area. I should have said that, sorry, I forgot. So here in particular, we see that if A is small, then this is the minimal area 1. But if it's big, then this is the minimal area surface, which is homologous to A. And now, Artie, I want to emphasize here, this is enough maybe to see why a homotopic isn't good enough. Right? So this can't be smoothly deformed to these two, but it's homologous to these two because chi A is sitting here. So then here, the entanglement wedge is like this, whereas the causal wedge still would have just been these two things, but made a little bit bigger. So let's put a dashed line here. So then, what entanglement wedge reconstruction is saying is that this region in the middle here can still be reconstructed in A, even though it's outside the causal wedge. And it's clear that you're not going to be able to do that by solving PDEs. Because from the PDE point of view, you don't care about this other region. Okay. Let me do one other example. So
you're going to tell us later how, if it is not PDE, then.
Yeah. Well, actually, let me make one comment on that now. So in the tensor network model, you can already see that you can do this in that model. Because remember I had this point in the center and I sent it out in these three directions, but there was nothing that said that I had to send them all out next to each other, right? So I could have sent two this way and one the other way. And then I could have arranged a situation where I reconstructed it on two separate regions where either one by itself I wouldn't have been able to get.
But will you be able to give us a formula for strong coupling in
there'll be a formula that requires you to know things like the ground state wave function, will expressed in terms of the field strengths in the CFT. So if you know that, then it's a great formula, but you probably don't know that. Formally there will be a formula.
But couldn't we try to get a formula in the following way, that we compute the entanglement with and without the action of that operator in the middle, and we see in the boundary theory how that changes, somehow reconstruct the operator with that?
We'll do something like that.
All right. That seems to be the general spirit of that the entanglement cares of this whole region. So if you Okay.
Okay, so just the last example, which I wanted to discuss, was the two-sided wormhole. So, and then where we take A to be just one of the boundaries. So here's a bifurcate horizon. So here, in the thermal field double, the two are the same again. So C of A equals W of A, and it's just the right exterior. But what I wanted to emphasize was that if instead of considering the thermal field double, we consider one of these longer wormholes that you get by putting matter in the middle. So for example, as studied in one of the million papers by Steve Schenker and Douglas Stanford. So then the horizons are like this. And then, well, we know the causal wedge always has to be outside of the horizon, because the causal wedge, right, D of A, here in the whole boundary, can receive signals from everything in the causal wedge. So it's never going to be able to receive signals from behind the horizon. And that's a general fact. Causal wedges can never go behind horizons. So C of A is sitting here, outside. But the entanglement wedge, actually, so the minimal surface is actually, in these geometries, is still sitting in the center there. So the entanglement wedge actually makes it all the way in to the center. So horizons are not barriers for entanglement wedges. And that's very interesting, right? Because obviously knowing what's going on behind horizons is interesting. So anything that says that we can, we thought we couldn't go behind the horizon and now we can is interesting.
Sorry, I should know this, but these examples of Schenker and Stanford are what they have stuff inside. Is it falling into the black hole, or and that sort of grows the?
Yeah. So they use these shells from the left and right that then are sort of going backwards and forwards in time to arrange a situation where the final output of the process is wormhole is long, and then there's some kind of matter inside.
Here your A was one whole. The whole boundary.
Yeah, the whole boundary on one side, yeah.
Now suppose I made it a little less than the whole, you would still go almost all the way to the inside?
Oh, the entanglement wedge?
Yes. Presumably it's continuous, right? I mean, I can see that
no,
the whole...
it's not continuous. You see here it's not, right? So in this example, I made A bigger, it jumped discontinuously.
But does it jump only when the whole thing closes off?
No, so already here it doesn't. Right?
Yeah.
So what happens, so right when we're at the symmetric point here, or a little bit below the symmetric point, the surfaces are like this. And then once we get past it, even by a little bit, the surfaces jump discontinuously to be in here. Because we have this competition between different...
I understand. But going back to that case where you start wrapping almost all of the sphere.
Yeah, so here I guess I would guess it's continuous, because I don't really see what the alternative competing extremal surface would be.
So if you wrap almost all of the sphere, it would already have gone beyond your positive.
Yeah, that's right. I think so. Yes, that's right.
Of course, we'll wrap only a small part in that.
Yeah, that's right. Yeah. Okay.
There is known from the work of Hartman and Mallinson. You have a small subset of the boundary on both sides, and there is an exchange of dominance for finite size of that thing, and then the geodesics start going through the.
You're talking about something here and something here, right?
Yeah, that's where you have two.
Ah,
Yeah,
okay.
there you go.
You're talking about O1,
Yeah. Okay, so, all right, good, we got to the end of our third lecture. On to lecture 4. Okay, so Rhett.
So on to lecture 4 in lecture 3. No, this is lecture 4.
This is lecture 4,
Sorry.
but we're now starting lecture 4, 2 hours into lecture 4. Okay.
Despite the fact that there were no questions.
Oh, actually, before I do that, though, I wanted to make one. What I was going to say now. Let me say the punchline of lecture 4 now, and then we'll do lecture.
Not all of us will be in that lecture.
Frankly,
Anything important, please say. Yes.
So okay. So right. So now the big result, which will be the goal of lecture 4, or the main goal of lecture 4, is that entanglement wedge reconstruction is equivalent to quantum Rutachinagi formula. So you can't have one without the other. So if the quantum Rutachinagi formula is true, then entanglement wedge reconstruction is true. And conversely, if entanglement wedge reconstruction is true, i.e. if we have an error correcting code, then there will be a version of the Rutachinagi formula which is also true. So this both says that quantum error correcting codes will always have the Rutachinagi formula in some form, and it says that if you have the Rutachinagi formula, S in holography was derived by Lipowitz and Montesano, then you must also have this entanglement wedge reconstruction.
Within what framework is this theorem proven?
Van Wenden algebras.
So just in any conformal field theory, for instance, this is true.
Yeah. But in a non-holographic CFT, neither side will be true, so it won't be very interesting. So
Daniel, can I ask something? Wasn't this implicitly also the message of the JLMS paper that bulk relative entropy is boundary estimate?
Oh, okay, yeah. So if you want to ask about JLMS, then let me put this.
Okay.
They say bulk relative.
Bulk relative entropy and boundary relative entropy are the same. Yeah, so actually that pops up sort of somewhere in between between these two. But all three of these are equivalent.
But bulk relative entropy of two states vis-a-vis the Ryu-Takayanagi formula, right? You have to say which region you're computing the bulk relative entropy.
Yeah. So the statement is you fix a boundary sub. Well, okay. Now I guess not everyone knows JLMS, but you say you fix a boundary subregion.
Right.
You pick two states. You look at the relative entropy of the reduced states in the CFT on that region, and the claim is it's the same as the relative entropy in the bulk on this chi sub A.
I mean, the two Ryu-Takayanagi surfaces will be different for the two states.
Yeah,
Is
but
that
not by much.
But that's what I'm saying. There's some in their thing that doesn't change. It's some
And order G to the 0, it sort of doesn't change.
yeah. So it's some perturbative statement, right?
Yeah, but remember, so I said I'm going to be working at order G to 0. So I haven't described. I mean, I haven't given you the precise versions of Ryu-Takayanagi. I mean, to prove a theorem, I'm going to have to be very precise about what everything means, right?
Okay. So you will be.
I will be.
All right. Good.
Yeah. But on behalf of the people who won't be here,
But you're not going to use your tensor network theorem.
No, I am not. So the theorem will apply to holographic CFTs. That was the whole point of the paper, is I wanted to emphasize that what happens in the tensor networks is not restricted to the tensor networks. That's just a general result of my quantum error correction. Okay. And so the title I gave to the paper was the Ryu-Takayanagi formula for quantum error correction, because somehow I already knew this direction, so then I was more interested about that direction. Right. And I should say that the references for this, so a weaker version of this way was we did with Shi, Dong, and Aaron Wall, and then the full version of this is from a paper by me last year. Okay. Good. So let me now erase and start over. puzzling features of AdS CFT, right? There's this radial commutativity, there's this subregion duality, and there's this Rutak-Yanagi formula. And I mean, from my point of view, all of those were sort of counterintuitive. From the CFT point of view, we've now seen that the first two make sense, can be explained from the point of view of quantum error correction, and now I'll try to convince you so can Rutak-Yanagi. So to start, as usual, let's see how it works for the 3Q trade code. Let's see how we're doing when we finish the 3Q trade code, and then probably what we'll do is we'll see that it's true for the 3Q trade code, and then the people who want to see the general algebraic formulation will have to wait until Thursday. Well, let's see how far we get. If somehow there are no questions about this, then
Sorry, are you finishing soon? We have a general club at 1.
Okay.
That's
Thank you.
it.
We didn't realize that. Okay.
We'll finish that.
we'll finish more or less by 1.
Oh, we didn't know this.
We have to at least explain this.
Yeah.
We should at least define the RT for this.
So that's saying something.
Yeah, what?
Sorry, we have a string left now. We disconnect, but deputy flow and we'll try and join again on Thursday.
Oh, okay.
Okay.
All right, that's fine. It should just be 10 minutes, but even that is too much.
Okay, fine. Okay.
We have to leave in 10 minutes too, so.
Okay, fine.
Yeah.
Go on.
Okay.
Thanks a lot.
This is India, right? Everything is flexible. Okay. So recall that in the 3Q trig code, we had this formula like that, where pi was 0, 0 plus 1, 1 plus 2, 2. Okay. So the mixed state version of this formula, so now if we consider a mixed state on the code substate instead of the pure state, just says that the encoded mixed state is gotten by conjugating rho on the first qubit, pi on the second qubit, with U12 dagger. Okay? Fairly obvious. So, good. So now to study the Rutak-Yanagi formula, what we want to do is we want to compute the entropy of this state on a subregion. And so by symmetry, so the interesting things, right, are to do either 2 or 1. Right? So let's first compute S rho tilde 3. So since we're doing rho tilde 3, the U12 is irrelevant, right? Because we're tracing out 1 and 2 anyways. So we just have this product state. But then since we traced out 1 and 2, we can forget about this and we just split chi in half. So we get log 3. Right? From half of this maximum mixed state.
Sorry, just let me make sure. Your point is that, well, clearly U12 of course does nothing and the rest is in something else. Yeah.
Actually, I didn't get it. What happened to that row 1?
So I traced out over 1 and 2.
So rho 1 only acts on the first.
So rho 1 only acts on the first Q trig.
Uh-huh.
And I'm computing the entropy on the third Q trig. So I trace out rho 1 and I trace out half of chi. Similarly, we can compute S of rho tilde 1, 2. So again, the U12s are irrelevant. Now because the entropy is invariant under unitary conjugation.
Right.
So we're again just left with computing the entropy of this. So now again we get a log 3 from the other half of chi. But now we get a contribution from here. We get the entropy of rho 1. But remember, rho 1 as a matrix is the same as rho tilde. They have the same eigenvalues, right? Because it's just it's the unencoded versus the encoded state. So this is just S of rho tilde. And hey, look, this is the Rutak-Yanagi formula. So if we define this L sub A to be log 3, then this is RT. Where maybe I should remind you. So RT, I shouldn't have erased it. So here we're saying that the area operator is log 3. So in the case of 3, you see there's no points in the entanglement wedge of 3. So this bulk entropy contribution is going to be 0 because there's nothing to contribute to it. And we've just got the area term sitting here. Whereas for row 1, 2, there is a point in the entanglement wedge. So we need to include its entropy. So apparently in this 3Q trig code, the Rita-Kinagi formula is exact for all rho tilde acting on the code subspace.
Provided LA is log 3.
Provided we interpret LA as being 1. So let me just make a few comments about that, and then we can postpone all the generalizations the next time. So first of all, note that the area term is coming from the entanglement in chi, which is what I advertised yesterday. And moreover, remember that the entanglement in chi is necessary for this to be a good code, in the sense that we can reconstruct either on 1, 2, or 2, 3, or 1, 3. So this entanglement, from the CFT point of view, is sort of this entanglement structure in the tensor network, right? It's kind of the entanglement, right? So like from the tensor network point of view, this is kind of like the dangling legs, and this is kind of the sort of contracted legs, right? So it's sort of the entanglement of long energy states in the CFT, and the fact that it's large is what gives rise to the fact that the area term is sort of dominant in that case. Here there are no ends, so they're competing, but it's just the kind of idea. Okay. Now there are a few things. I should also say this argument more or less can also be made for the tensor network happy code, and so that's one way of seeing how that the Rita-Kinagi formula has to work there. Although there are some annoying edge effects as I discussed, so you mentioned, so you sort of miss by a little bit sometimes, depending on the Dorset function.
What is the role of log 3 there? Some dimensionality of
so basically, so you fix it. Yeah, so you fix. So basically, it's the dimensionality of the indices. So it'd be log 2 there. But then you also get a factor in front from the area, right? So here there's only one option for the area, so they're all the same. But there,
it's the area.
but there it's the length of the. So you pick the boundary region, and then there's a geodesic cut that goes through the network from one edge of the boundary region to the other. And then you get the number of links, which is cut times log 3. And basically, each time you cut a link, it's like with this chi. You're cutting a certain piece of the chi.
5 plays no role in the formula.
5 plays no role in the formula. Yeah. I mean, other than the fact that the graph geometry involves 5. Yeah. Okay. So then more or less this argument also works there. So that already suggests that this is going to be fairly general. Let me just comment on 2 bad features of this, one of which is already fixed in the tensor network and one of which isn't. So one bad feature here is that there's only one bulk point. So either it's in the wedge or it's not. And if it's in the wedge, then there's nothing in the complement, right? So basically that's saying that every state and all the information in the code subspace can be reconstructed on this A, and none of it can be reconstructed there. So that's the conventional definition of error correction, but it's clearly too strong, right? Already in the tensor network, right, what was happening is that some information can be reconstructed here, and the rest can be reconstructed there. So you get sort of partial reconstruction of the information, right? So I mean, we want that, right? I mean, already in Happy we had that, but then clearly, for this RT story, right, that shows up in that there will now be a bulk entropy term also. And finally, most annoying perhaps, is that this is kind of a stupid area operator, right? It's a C number. It's the same in all states in the code subspace, right? Whereas the real area operator is of course not a C number. There's different states in the code subspace have different areas. So we better make sure that when we generalize it, that we see that the quantum error correction machinery is flexible enough to allow for the area operator to not be a C number. And we'll see that it is. Okay, so maybe I should now stop.